I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast that helps you understand the chemistry of your everyday life.
Jam, how are you doing? What's up?
I'm good. I'm surviving this 2021 so far.
Yeah, 2021's a little wild straight out the gate.
I know. I thought maybe day one it'd be just brighter, better, But so far, I guess it's going to be gradual, maybe? I don't know.
Maybe, yeah, probably a gradual improvement, incrementally improving things.
Yeah, let's hope. Let's hope for that.
Well, speaking of incremental, that kind of incremental change does kind of play into our topic for today.
Oh, interesting. Okay, cool.
So that was a fun segue.
What is it?
So we're going to be talking about, I forget that people who have the podcast already know this, so it's not a surprise for them, but it is for you.
Right.
Is glass a liquid?
Oh, nice.
So we got this question once a long time ago, and I don't, unfortunately, have the listener's name written down, which I'm so sorry. But then it came back up when we were visiting Mr. Hollis's class. And
that's right.
I knew I was going to have to dedicate a whole episode to this at some point because it was just too much for one little Q&R. We try to keep those quick and light. And this is kind of a more complicated topic. So I felt that the time had come. And if that listener who asked the first time, I think it was close to a year ago, if you're out there still and you're listening and you're waiting patiently for your question to be answered, hit us up on Instagram and we'll shout you out in the next Q&R because it's hard to search those messages to find those questions. So
yeah, totally.
So before we talk about if glass is a liquid or a solid, first we have to talk about what a liquid and a solid even is. And I don't think we've talked about this before.
I don't think we have either. I feel like we've ended up talking about gases a lot.
Mm-hmm.
We've gotten a little bit more into that, like liquids into gases. But I guess we haven't talked specifically about the differences between solids and liquids that I can remember.
I don't think so. So I'm sure a lot of people learned the basic ideas of this in class when they were younger. But at the molecular level, a solid's molecules are held rigidly close together.
Mm-hmm.
So there's not a lot of freedom of motion. The individual molecules can vibrate and they can absorb and re-emit energy. We've talked about that. So there is a little bit of wiggling motion is what I'll call it. The little bit of, sometimes it's called translational, vibrational movement.
Mm-hmm.
But there's not going to be an atom moving past another atom or a molecule moving past another molecule. They're sort of stuck in place.
Relative to each other.
Right.
They don't really move a ton.
Right.
Okay.
Now, a liquid's molecules are held close together, but they are less rigidly close. So they can move past one another. They'll stay together in this one form as a liquid, but they are able to take on the shape of a container, for example. They're able to shape shift some, and the atoms and molecules can move past each other.
Okay.
Now, a gas's particles, we've definitely talked about this. A gas's particles are not close together at all. They are very spread apart in a space, and they will expand to the fullest extent of whatever container they're in. There's a funny part on Parks and Rec where Andy Dwyer just pulls that fact out of nowhere and says, a gas will expand to fill the shape of the container it's in, or whatever. And it always makes me proud because he's very accurate, and it's so unexpected from Andy. So the thing about solids, those molecules aren't really moving.
Mm-hmm.
But when the solid initially forms, they can be arranged in different ways.
Okay.
So you can maybe think of this like blocks, like from kids' blocks. You can arrange them in a whole number of different ways, but they're still going to be blocks.
Right.
And you've experienced this, although you may not expressly realize it, because you've seen graphite, which is pencil lead, and you've seen diamonds. Both of those are different arrangements of carbon.
Oh, interesting.
Just carbon atoms. We'll probably have a whole episode on that.
Uh-huh.
So the different way that the solid forms can have really different properties. You can have something sparkly and beautiful that's highly ordered, like a diamond, and then you can have something like graphite.
Right.
Okay, so what glass is what's known as an amorphous solid.
Okay. That sounds very cool.
It is very cool. It's not a liquid.
Okay.
It's a solid. But it's not formed in a crystalline state. So solids can be broken down into crystalline, which is highly ordered. They call a long range order.
Mm-hmm.
So think of several repeating units over and over again. Say they form a cube-like structure. All of the atoms are arranged in cubes and they're stacked side to side and on top of each other as far as the eye can see if you shrunk down to be the size of the atom.
Mm-hmm.
That is a highly ordered, also known as a crystalline structure.
Got it. Okay.
To think of a snowflake, that has a lot of order. It's very crystalline.
Mm-hmm.
Now, the other kind is an amorphous solid. So in that case, it's cooled very quickly, past the point of being a liquid.
Mm-hmm.
But because it's cooled so quickly, it doesn't have time to get ordered. It doesn't have time to get itself organized.
Got it. Okay.
So instead of this nice, rigid, consistent order material, it's sort of wacky. It's almost just like you took it in its liquid state, and wherever it was in its liquid state, you hit a button and froze it there.
Gotcha.
So usually as solids form, they'll take the nice, whatever basically is the most stable formation, they'll make that. And that's why it forms these repeating units of similar structure over and over and over again, every which way, is because it's the most energetically favorable. It's the most stable position.
Mm-hmm.
But if it doesn't have time for that to happen, it will just freeze wherever it's at.
Got it. So you mean like it's in a liquid form, like it's really hot, and then it cools down below like the melting point of whatever.
Yes.
That is. And then, okay, got it. So like glass, for instance, obviously can be liquid or solid. Okay. I think I'm tracking.
But if you cool it very quickly, it won't have time to be nice and crystalline. So an example of that you may have seen in real life is if you boil sugar in water and you hang the rope or the stick down, you can make rock candy.
Oh, yeah. Right.
But you have to really wait a while for that to happen. You leave it out on the counter and you leave it there for days and days, and it grows over time, right?
Yeah.
You can't really speed up that process by throwing it in the freezer.
Right.
You might get some sugar globs, but it's not going to be those beautiful rock candy formations. It's kind of the same thing with glass. So glass is made by, generally, you have silicon dioxide and some other salts or molecules. So a very common one, silicon dioxide, sodium carbonate, and limestone. And you heat it up, and in that molten state, you combine them and then cool it very quickly so that it very quickly goes into the solid state and it doesn't have that crystalline structure.
Which I guess is great for it being really easy to see through in some ways. It's like liquids are easy to see through too, a lot of times.
Yeah, I wonder if that's true. One of the students asked me if I knew why glass was see-through, and I don't. But I wonder if that has something to do with it.
Because they obviously it had a lot of structure going on. It might have things that make it
be more solid.
Sorry, yeah.
Yeah, I don't know what those structures would look like if you took silicon dioxide, and I guess that would be quartz, and that is more opaque.
Yeah.
Good thought, Jam. That's a really good, look at you. Scientific mindset over here. That's true. I wonder if that's part of how glass is see-through. So if that student from Mr. Hollis's class is listening, there's one of your answers. That's so exciting.
Nice. It's like this chemistry thing is kind of slowly rubbing off on me a little bit.
It's starting to stick. You caught something that I didn't even catch, so that was good.
Just formed a little hypothesis, if you will.
But the thing is, molecules are happier in a crystalline structure. So amorphous solids, if given enough energy, can sort of migrate into trying to form a more crystalline structure over time. Now, they have to have enough energy to do that, which for glass, you'd think, oh, that's why we've seen, those windows that are thicker at the bottom than they are at the top because they flow over time.
Mm-hmm.
That's actually not true.
Oh, okay.
A study came out, I think it was about 5 years ago, that revealed that the glass in cathedrals, that's thicker at the bottom than it is at the top, stained glass windows, that looks like maybe it's flowed over time. The movement of the molecules is so slow that we would not be able to see that change in our lifetimes.
Whoa. Weird.
Yes. So it's actually more likely that those windows were just formed slightly thicker on one side.
Huh.
It's kind of sad.
Yeah, seriously, that's weird, dude. Because that's I think probably the whole reason why a lot of us have ever heard that maybe glass is a liquid in a way, or not a normal solid, because we've heard of, I've heard that talked about old buildings and the glass being thicker at the bottom. But maybe that was even the case, maybe who knows how they made windows then, but maybe it was just an inherent part of the process where it happened to happen that way. Maybe the glass wasn't fully cooled. They set it up. And then while it's still really hot, that happens before, before it's cooled. Who knows? But that's the whole reason I've ever heard that maybe glass is weird.
I know. Isn't that shocking?
Seriously. But it would happen in a long enough timeline, basically, just way longer than we live.
Yes. So it would happen in a long timeline. It would happen to where it would probably move to a more ordered state if enough energy was put into it over time. Let me make sure I can find that article real quick. I was just looking at it, but it was published in the Journal of the American Ceramic Society. Isn't that so wild that exists?
Yeah, I want to be a part of one of those societies. I'm like, man, these exist out there. People are living it up, having a ball in these societies, and I'm not part of one.
That's funny.
I need one.
So in the Journal of the American Ceramic Society, that's where they published this information. Mm-hmm. In 2017, they basically said that using their analytical experiments, they found that the flow would calculate to be about 1 nanometer over 1 billion years.
My gosh.
I know.
There's no way. I mean,
there's no way.
Stray baseball would shatter that window much sooner for most of those situations than
absolutely.
It would ever get a chance to flow that much.
Yes. And now I think they specifically tested that kind of glass, so it may be different with different kind of glass, but the transition temperature where it would begin to flow is much, much higher than at room temperature.
Wow.
So that observable flow of glass would just take so long for us to actually see it. So that's actually just a myth that we kind of all believe.
Dang, interesting.
But
it accidentally led us to something that's sort of true about glass that's different than other solids. So that's kind of interesting.
Yeah. Isn't that?
Yeah. We were able to disprove the thing that actually still proves something that is still true about glass in a way. Huh.
Yeah. Well, here's a place where this also occurs on a much more lifetime scale. Many pharmaceuticals are also amorphous solids because that allows them to dissolve more easily in your body.
Okay.
And the reason they have expiration dates is because they have a much closer to room temperature transition. So at room temperature in your cabinet, they will begin to become more crystalline over the course of a few years instead of 1 billion years. And that will make them more difficult to dissolve in your system, and they basically become useless.
Oh, so you're talking about just pills and stuff that do that?
Yeah, just drugs. And some kinds of drugs are amorphous solids.
I'm pretty sure I've seen an old bottle of Advil or something get kind of crystally before. Not crazy, but just it was definitely old,
Yeah.
Wow.
So we don't see glass flow over our lifetime, but you could see your medicine flow over a lifetime.
Almost as cool, if you think about it.
Almost as cool. And it seems glass seems like it should be liquid, but it is different, like you said, than most solids, but it's not exactly a liquid. And its flow rate is really small. So that was a myth
Yeah. Dang.
Okay, so if you want to take a stab at giving that back to me, just so we can make sure you're tracking, then I have some more fun facts for you.
Okay. I think I can do this.
Okay.
So we've talked a lot about gases in terms of the different states of matter. That's kind of been what we've talked about a lot, where the particles, the molecules in a gas can spread out a lot. So they want to, they're all over the place.
Mm-hmm.
And then in a liquid state, they are all together, but they are really free. They're free to move kind of past each other.
Right.
But they do stay in a mass if they can. So that's why they fill a container. You're not just setting your cup of water on the counter and it's like floating all over the place.
Right.
Unless you're in the International Space Station, in which case I feel for you.
I don't know. I think they probably have gravity makers on the International Space Station by now, don't you think?
Oh, that'd be cool. Wow, I've not thought about that.
I just assumed they did, but maybe that's because I watched too much Xenon, the sequel, as a child.
I think, well, at least a lot of the videos I see from astronauts, they do a lot of the water tricks, just for fun. But
yeah,
but it stays together, and it's not trying to expand, but it does take the shape of its container in a liquid.
Right.
And then solid, things get much more rigid, especially once it already becomes a solid. Once it's in whatever shape or structure it's in, it's really hard for that to change. There might be like slight movements of the molecules, but relative to each other, they don't really change a lot. They're not able to move past each other like they can in a liquid.
Right.
But the difference being that solids can have very different structures from each other, even though they're all still solids.
Right.
And the most ideal is for solids is a crystalline, highly ordered structure because it's very stable.
Yes.
And in many cases, like the difference between diamonds and graphite, it's also much stronger. It's got a lot more going for it in that realm. But with glass, it is a liquid when we're trying to do stuff with it and combining the elements that make up glass, which is, you said, silicon, oxygen.
Silicon dioxide, actually. It's one thing. It's in sand.
Right. So they combine, you said something like sand and limestone and...
Pretty much,
okay.
Yeah. Silicon dioxide, sodium carbonate, and limestone heated up.
Okay. So they heat it up to be able to turn it into liquid to do what they want with it. And then, obviously, once you get it into a shape of some kind, either a vase or a window or whatever, you want it to stay in that. So they cool it quickly so that the work they just did stays. And that means that its state as a solid is not crystalline because that takes time to happen. And it's in a much less ordered state, which to me reminded me of what it's like to study for a test versus cramming for a test.
Mm-hmm.
If you take time, say across a week, where you study a little bit at a time, you get time to build your knowledge in a more organized way that makes you feel much more structured, much more prepared, much more strong in your preparation for a test. But if you try to cram in like the last little bit, you might be able to review a lot of information. You might be able to look at tons of stuff, but it's going to be so fast and it's going to be very disorganized that the state you are in your mind, we all have experienced this. We've experienced the times where we have studied a lot, and we've experienced the times where we've crammed. The state of our minds when we walk into that test, when we've studied for like a week or two in regimented, structured ways versus when we crammed, could not be more different.
That is so true.
And then it's like we've got this building, like nice structured thing of knowledge. We walk in, we feel much more prepared, much better. Or we feel like, oh my gosh, I just flew through pages of a book and it's all kind of maybe in there somewhere, but boy, am I going to have a hard time like figuring it out.
Yes. That's good.
So that's kind of an emotion related analogy. It doesn't give us a picture as much as it does a feeling.
This is good because it combines two of my favorite things, which are human learning theories and chemistry. You know, that's my new research area. And that is true. Actually, studies and research clearly shows that if you practice a little bit over a long range of time, you are going to be able to build connections and make a more organized knowledge map in your brain or concept map than if you cram. And if you cram, you're also going to lose that information much more quickly. So that is factually correct about human learning theory and a great illustration of the state of the molecules. You know, glass is very disordered compared to the highly ordered crystalline. The crystalline form of silicon dioxide is quartz. And there's a great picture in my textbook, which I think I can take a picture of and post it, that shows the structure of the molecules in quartz versus the structure of the molecule in glass. And one's nice and repeated and very ordered, and one's all wonky and crazy. And that's how your brain feels. You walk in, you're confident, you know this stuff and the way it relates to each other, or you walk in and it's all kind of like spaghetti in your brain.
Yeah. So it's like, and then that would explain too why it's kind of still moving. You didn't build a solid structure of knowledge. It's a kind of not super solid, not super dependable blob of knowledge that you have that is going to be easy to kind of move and melt and not stay in your brain.
That's so true. That's good.
But that's also in general just crazy about glass to think about it that way.
Yeah.
That, I mean, I just thinking that it is really disordered because it's such a, to me, I guess I would have thought initially that maybe it has a higher order because it's a perfect thing to see through. But I don't know. It's interesting. I'm very fascinated that that's the case and that it's a really disordered, not ideal for solids material, but very ideal for us and what we use it for.
Right.
You know?
Yeah. Yeah. Well, I'm going to tell you even more about glass. So one of those students asked why we use glass in lab. You know, we often use glassware instead of ceramic ware. One reason for that is that you can see through it. So, you know, you can see what's going on in your experiment. That's important in the lab. But another is that if you add different things to glass, you can change its properties. So you've seen that different colored salts can change the color of the glass. That's what stained glass windows are about. But also, if you add sodium borate, it will be more resistant to thermal changes. And so Pyrex, the brand Pyrex, when they first started, realized that if you could add sodium borate to their glass, it would be able to resist big changes in temperature. So, you know, now if you take you can't take a casserole dish straight from the fridge and put it into a hot oven. You want to let it come to room temperature and then put it in the oven. Because if you go straight from hot to cold, it'll just break. Or you're not supposed to put your glass baking dishes right under the, not the broiler, but the preheat setting on your oven because it's so hot trying to heat up your oven that it could break the glass going from room temperature to that hot.
Oh, interesting.
But if you add sodium borate, it is resistant to that. And Pyrex originally had that. So you could take it from the freezer and put it in the oven. It would be fine.
Wow.
So they use that to make glassware for labs. Same Pyrex brand that you see in your kitchen. They would use that sodium borate to make it more resistant to heat. So you could take something directly from a boiling, bubbling, hot reaction and plunge it in an ice bath and immediately cool it down, and the glass doesn't break.
Wow. Dude, wow.
But unfortunately, Pyrex actually sold off their kitchenware division, so current Pyrex doesn't have that same property.
Really?
Really. But old Pyrex does. Because you don't really need them to be that resistant to change in your home setting the way you do in the lab. But the lab Pyrex does still have that sodium borate in it.
Interesting. Yeah, that's crazy. Wow. I kind of wish it did just because it sounds like cool. It sounds nice to have that ability.
Well, you can try to go to thrift stores and get old school Pyrex, and maybe that would still have it.
Mm-hmm.
Also, another way you can change glass's properties by adding something to it is you can add lead to glass, and it is more sparkly. It changes the refractive index, which we've talked about that in a previous episode.
Mm-hmm. Yeah. Dang, yeah, I forgot about that.
So glass is not only amorphous, but it also can be tweaked and changed and has a lot of cool history to it.
Interesting. And so does the nature of its structure make it, or lack of structure, I guess, make it a little bit more conducive to have things be added to it that affect it that way?
I can't confirm that anywhere from any source, but I suspect that is the case, is that because it's not highly ordered, adding something into it isn't disrupting this high order. You know, if you took a diamond and you shoved a different kind of molecule in there, you could see that imperfection. It's a mess up in the beautiful order of the diamond.
Right.
But this isn't ordered to begin with. So I think because you're not messing with this beautiful order, it's kind of fine. And it can kind of take adding different things. That's my suspicion. I can't confirm that, though.
Got it.
That's just off the cuff, chemistry brain talking.
Interesting.
So that's my fun stuff about Pyrex for you. Fun information that you earned with your awesome analogy. So good job, Jim.
Thank you. Is it time now to talk about our weeks, maybe what we can see through them?
Oh. I think it is. I think it is time to go through the looking glass of our weeks.
There we go. That's a good one.
I did one.
Nice.
Nice.
It's like sometimes you need to put your week under a microscope and really take a look at it. And,
That brings a whole other question to my mind about if microscopes, how they make the magnification. Doesn't matter. Okay. That's a different topic for a different day. So yeah, is there anything good about your week you want to share with us, Jam?
Yeah, so for us, this is kind of a mix of things. It's not like just good or bad, but my wife and I have been working on trying to move, not away or anything, but move into a different house. We feel like we're obviously very much into kid mode, having kids.
Mm-hmm. Yeah.
Don't want a ton of gap of time between them. And so we're wanting to make some moves to be in position to have kids and have some room for that and stuff. So we've been thinking about that for like a few months. And now we've really got the gears turning on that process, which is fun, but stressful. And
yeah,
it's not necessarily the most exciting thing because we do like the house we currently live in. But it just feels like a change we need to make. So that's been interesting. And we have been working on that and been looking at houses with our realtor who we really like a lot, who, shout out, used to be my barista.
Whoa.
He was one of the owners of the coffee shop that I loved that sadly closed due to COVID in, I guess, what was that, like May or June when that happened? I can't remember exactly when. But anyway, he became a realtor before any of that happened and had started doing that. So he's my realtor. He's awesome. His name is Ben. And so that's been pretty fun. And we have a house that we're have an offer on right now that we're working on and stuff. So and
it has a really nice backyard, so you and I can hang out socially distanced all day.
Yeah, so we'll see. Yeah, exactly. That'd be awesome. We'll see if that one works out. We're in just like under contract, getting things inspected and stuff. But so that's been occupying a lot of my mental space when I have not been working or podcasting or anything else. But what about you?
So I had the opportunity for the first time that I can ever remember doing this in grad school, ever, to take 2 weeks completely off.
Wow.
And I planned ahead. I got all my work done early and very safely with all our COVID restrictions. We got to spend time with my family, and that included a lot of quality time with my nephew, which was really special.
Mm-hmm.
And we even got to go to Amarillo for a few days and see Mason's family, and we got to go to the Helium Monument, which was very exciting. We took lots of pictures.
Awesome. Dude, can't wait to see those.
And overall, I think it was just really good for me to remember that the world can keep on turning if I'm not working. And it gave me a chance to be excited about coming back to work. So I think this is definitely the first time in over a year that I took a real break.
Nice.
But it was the first time in all of grad school that I've had 2 weeks where I did not think about work at all. And so that was just really a gift. And I know not everyone has that luxury, but I think making a habit from now on of not being on my work email anytime I have a vacation is going to be something that I make a priority, because it just gave my brain a chance to reset, and it gave me an opportunity to be excited about working again. You know, I took a real break, so I was looking forward to coming back to it.
Yeah. Yeah. That's awesome. Very cool.
Yeah. And I was really excited to come here and teach you about glass too. So thanks for coming and listening and learning all about glass.
And thanks for teaching us. Very fascinating episode. And this, like many of our episodes, is an idea, a question from you guys. So please send us your topic ideas, your questions, things you wonder about. Is this chemistry? This thing in my life? This question I've learned? This thing I've heard? This myth I've heard? Or is it a myth? I don't know. So if you have questions or ideas, reach out to us on Gmail, Twitter, Instagram, and Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your thoughts and ideas. If you'd like to help us keep our show going and contribute to cover the costs of making it, go to ko-fi.com/chemforyourlife and donate the cost of a cup of coffee. If you're not able to donate, you can still help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us to be able to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode can be found in our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to S. Navarro and A. Kiwasong, who reviewed this episode.